lecture. We're going to write the alveolar gas equation and explain its use. So what is the alveolar gas equation and why do we care about it? The alveolar gas equation calculates the partial pressure of oxygen at the level of the alveolus. This is important when trying to decide why a patient is hypoxemic. Patients can be hypoxemic because there's a problem in getting oxygen or delivering oxygen to the level of the alveolus, or there's a problem in transferring that oxygen across the alveolar capillary unit into the bloodstream. The alveolar gas equation is really just part of Dalton's law. Dalton's law, if you remember, is total pressure is equal to a bunch of partial pressures. And when it comes to the alveolar gas equation, the total pressure is the atmospheric pressure. And the partial pressures that are combined at the alveoli are the partial pressure of oxygen, that's P big A O2, which means partial pressure of O2 at the alveoli, plus the partial pressure of water in the alveoli, plus the partial pressure of carbon dioxide in the alveoli, plus the partial pressure of everything else, all the crap. Most of that is just nitrogen. Now we're going to rewrite that and make it look like the alveolar gas equation. I'm going to write it out for you first, and then we're going to go through each part in detail. So the partial pressure of oxygen in the alveoli is equal to the fraction of inspired oxygen times the pressure of atmosphere minus the pressure of water in the lung minus the partial pressure of CO2 over R. We're going to go through all of these in detail. Okay, so let's start with the fraction of inspired oxygen times the pressure of atmosphere minus the pressure of water. This is the inspired oxygen. This combines what's coming in from the atmosphere minus the water content that's in the dead space of the respiratory tract. Let's focus on the pressure of atmosphere. Remember, the pressure of atmosphere is actually the total pressure that comes up with Dalton's law. And the pressure of atmosphere can be normal, what I refer to as 760 millimeters of mercury. I just want to pause here and say that is a picture of an alveoli, not anything else. Or it can be much smaller than that. Think about if you're on Mount Kilimanjaro or Mount Everest. The actual total pressure in your lungs is smaller because the total pressure of the atmosphere is smaller. Or the pressure can be much, much bigger, as if you're in a hyperbaric oxygen chamber. So the first thing to think about when you're thinking about the alveolar gas equation is what is the total pressure that all the different components, the partial pressures, can combine to become. They can never be more than that total pressure. And again, the total pressure is always atmosphere. Now let's return to the inspired oxygen portion of the alveolar gas equation, FiO2 times the pressure of atmosphere minus the pressure of water. Now, water is not the water that's in the humidity of the air. Water is actually the water pressure in your lung component. And by definition, that is about 47 millimeters of mercury at normal body temperature. It just doesn't change, so it's a constant. So back to the inspired oxygen equation, FiO2 times the pressure of atmosphere minus the pressure of water. Now, what about FiO2? FiO2, as most of you know, is 21%. In the atmosphere, we have 21% oxygen, about 78% nitrogen, and 0.01% of other stuff. With that in mind, I want you to pause here and calculate the inspired oxygen. And I'm serious. I think you need to pause and calculate what the inspired oxygen that we all breathe in is at sea level and see what you get. And if you get the right answer, then you can assume that you understand this part of the alveolar gas equation. Pause. Welcome back. The inspired oxygen that we all inspire at sea level is 150 millimeters of mercury. That's the partial pressure of oxygen that comes into your dead space in your respiratory tract. Now we're ready to move on to the other part of the alveolar gas equation, the P little a CO2 over R. I think this is where it gets kind of confusing. And this is where I go back to basics. The alveolar gas equation is really just a combination of partial pressures that equal the total pressure, and the total pressure being atmosphere. So again, what are the partial pressures other than oxygen? You have the partial pressure of water. You have the partial pressure of nitrogen, which we calculate by using the fraction of inspired oxygen. And then you have the partial pressure of CO2. Where does CO2 reside? Well, in the alveolar gas equation, we say that it resides actually at the level of the alveolus. And for a normal human, the CO2 is 40 millimeters of mercury. So let's pause here and calculate the PaO2 now that you've gotten everything that's part of the equation. Pause. Come back when you're done. I was tricking you. You can't actually answer this question until you understand what R is. So let's take a sidetrack and talk about R, which is the respiratory quotient. The respiratory quotient is just something you have to believe. It is a combination of the CO2 production over the oxygen consumption. So what I mean is that for every oxygen molecule that you produce, you also produce some amount of CO2. Sometimes it's 1-to-1, sometimes it's less than 1-to-1, and sometimes it's more than 1-to-1. This is driven by what proportion of fats, carbohydrates, and proteins you eat. So for the mixed human diet, the traditional human diet, we say that it's traditionally 0.8. The R value, or respiratory quotient, is 0.8 for a normal human diet. What does all this mean for the alveolar gas equation? Well, the truth is this. The alveolar gas equation represents a steady state of O2 diffusion into the capillary and CO2 into the alveoli. It's never at any sort of stopped static moment. It's going in back and forth at all times. And this R value is what I like to think of as the fudge factor that allows for the alveolar gas equation to work. Again, I step back to basics. The alveolar gas equation is really just the thought that you have a total amount of pressure, the pressure of atmosphere, and you have to subtract everything out that's not oxygen, and what's left is oxygen. Again, what you subtract out is the partial pressure of water, the partial pressure of nitrogen, which you get by multiplying by the fraction of inspired oxygen, and the partial pressure of CO2. And that R value is the fudge factor that allows it to work. So now, calculate the PaO2. Really here, pause and do it. Welcome back. The P big AO2, the partial pressure of oxygen inspired at the level of the alveoli, is 100 millimeters of mercury when you take everything else out. Now let's go back to the learning objectives. We've talked about the alveolar gas equation, explained its use. We've defined the respiratory quotient for what's that worth. And now let's define the normal AA gradient for the partial pressure of oxygen. A, big A, means alveolar, little a means arterial. This is a really important concept to have, particularly when you're going into thinking about the concepts of hypoxemia. So the alveolar arterial gradient. Let's look at the schematic. You have a deoxygenated amount of blood going in from the pulmonary artery through the capillary, passing across the alveolar capillary unit and back out, oxygenated going through the pulmonary vein back to the heart. You've got P big AO2 in the alveoli, and you've got P little AO2 in the capillary. Another way to look at this is the electron microscopy again. You've got the P big AO2 in the alveoli and the P little AO2 in the capillaries. The difference that is normal in a healthy person is about 10 millimeters of mercury, meaning that if you have 100 millimeters of mercury in the partial pressure of oxygen in the alveoli, P big AO2 is 100, P little AO2 should be 10 less, about 90. Now, there are a couple things to think about. One is that the AA gradient increases with age, and it increases with FiO2. Let's go back to learning objectives and see how we did. Within anatomy and histology, we've talked about the difference between the total pulmonary ventilation and the alveolar ventilation. We've talked about the components of the alveolar capillary unit and how those components can affect gas exchange. And we've explained the role of surfactant. And within physiology, we've described the alveolar gas equation and explained its use. We've defined the respiratory quotient, and we've defined the normal AA gradient. What I'm not going to do, but I think if you can answer this for yourself, it means you understand the alveolar gas equation, is compare and contrast how VQ mismatch and hypoventilation affect the AA gradient. What happens when you have increased CO2 to the AA gradient? Does it get bigger? Does it stay the same? Does it get smaller? What happens when you have a problem at the alveolar capillary unit? Does the A gradient get bigger, smaller, or stay the same? If you can answer those questions, I think it means that you understand the alveolar gas equation. And with that, thanks for your time.